question is whether it is the intent of the code to require that a precast foundation be grounded. The answer is no. It is not explicitly required by code to ground a precast foundation wall. National Electrical Code Section 250.52 states that metal underground enclosures must be grounded. However, it defines underground enclosure as an enclosure that is buried below the surface of the earth. A precast foundation wall is not typically considered an underground enclosure since it is exposed above ground, at least partially. National Electrical Code Section 250.110 states that other non-electrical metal parts of a structure must be grounded if they are likely to become energized. This could include metal studs, joists, or other structural members. However, this section does not specifically mention foundation walls. The International Building Code does not contain any specific requirements for grounding precast foundation walls. American Concrete Institute Standard 318 Building Code requirements for structural concrete does not address grounding of foundation walls. While some code officials may interpret the codes as requiring grounding of precast foundation walls, there is no clear requirement in the National Electrical Code, International Building Code, or American Concrete Institute standards. As long as the grounding provisions, such as grounding electrodes and the grounded electrical system, are adequate, it is generally not necessary to ground precast foundation walls. In more detail, let's examine the NEC. The National Electrical Code, or NEC, is a regionally adoptable standard for the safe installation of electrical wiring and equipment in the United States. It's part of the National Fire Code series published by the National Fire Protection Association, or NFPA. While the NEC itself isn't law, it's often adopted by states and municipalities, becoming a legal requirement. The NEC undergoes revisions every 3 years to keep up with technological advancements and new safety practices. The NEC covers a wide range of electrical topics, from wiring methods and overcurrent protection to grounding and bonding. It provides detailed requirements for electrical installations in various types of buildings, including residential, commercial, and industrial structures. The purpose of the NEC is to protect people and property from electrical hazards. It sets minimum safety standards for electrical installations to reduce the risk of fire, electric shock, and other electrical-related incidents. The NEC contains specific requirements for grounding and bonding electrical systems. Grounding connects the electrical system to the earth, providing a path for fault current to flow back to the source. Bonding connects different metal parts of the electrical system together, ensuring that they are at the same electrical potential. Proper grounding and bonding are essential for safety, as they help to prevent electric shock and reduce the risk of fire. The NEC addresses the grounding of metal enclosures and equipment. It requires that metal enclosures be grounded to provide a path for fault current in case of a short circuit or ground fault. This helps to protect people from electric shock and prevent damage to equipment. The NEC also covers the grounding of metal parts of buildings and structures. It requires that metal parts that are likely to become energized be grounded to minimize the risk of electric shock. This includes metal siding, metal roofs, and metal structural members. Section 250.52 of the NEC specifies the types of grounding electrodes that are permitted. These include metal underground water pipes, metal frames of buildings and structures, concrete encased electrodes, and ground rings. The NEC provides detailed requirements for the installation and connection of grounding electrodes. Section 250.110 of the NEC addresses the grounding of non-electrical metal parts. It requires that metal parts that are likely to become energized be grounded to prevent electric shock. This includes metal fences, metal gates, and metal equipment housings. Let's now consider the International Building Code. The International Building Code, or IBC, is a model building code developed by the International Code Council, or ICC. It is a comprehensive set of regulations for the design and construction of buildings and structures. Like the NEC, the IBC is not a law itself, but it's widely adopted by states and local jurisdictions in the United States and around the world. The IBC covers a wide range of topics related to building safety, including structural design, fire safety, accessibility, and energy efficiency. It provides detailed requirements for building materials, construction methods, and building systems. The purpose of the IBC is to ensure the safety and welfare of building occupants and the public. It sets minimum standards for building design and construction to reduce the risk of structural failure, fire, and other hazards. The IBC addresses the structural requirements for foundations, walls, floors, and roofs. It specifies the minimum load-bearing capacity of these structural elements and provides guidelines for their design and construction. The IBC contains requirements for fire-resistant construction. It specifies the fire resistance ratings for walls, floors, and roofs, and provides guidelines for the installation of fire-stopping materials. The IBC addresses accessibility requirements for buildings and facilities. It specifies the minimum requirements for accessible entrances, restrooms, and other features to ensure that buildings are usable by people with disabilities. The IBC also contains requirements for energy efficiency in buildings. It specifies the minimum insulation levels for walls, roofs, and floors, and provides guidelines for the installation of energy-efficient windows and doors. While the IBC doesn't specifically address the grounding of precast foundation walls, it does address the grounding of metal building components. It requires that metal building components that are likely to become energized be grounded to prevent electric shock. This includes metal siding, metal roofs, and metal structural members. The American Concrete Institute, RSI, is a non-profit technical society and standards developing organization. Its mission is to develop and disseminate knowledge for the best use of concrete. The ACI develops and publishes standards and other documents related to concrete design, construction, and materials. These standards are widely used in the construction industry and are often referenced in building codes. ACI 318 is a building code requirement for structural concrete. It provides detailed requirements for the design and construction of concrete structures, including buildings, bridges, and other structures. ACI 318 covers a wide range of topics related to concrete, including materials, mixed design, reinforcement, and detailing. It specifies the minimum requirements for the strength, durability, and serviceability of concrete structures. ACI 318 addresses the design of concrete foundations, walls, columns, and beams. It specifies the minimum reinforcement requirements for these structural elements and provides guidelines for their design and construction. ACI 318 contains requirements for the design of concrete slabs and pavements. It specifies the minimum thickness and reinforcement requirements for these elements and provides guidelines for their construction. ACI 318 also addresses the design of concrete structures for seismic resistance. It specifies the minimum requirements for the design of concrete structures in earthquake-prone areas and provides guidelines for their construction. While ACI 318 does not specifically address the grounding of precast foundation walls, it does address the corrosion of reinforcement in concrete structures. It specifies the measures that must be taken to protect reinforcement from corrosion, including the use of corrosion-resistant reinforcement and the application of corrosion-inhibiting admixtures. Grounding can affect corrosion in reinforced concrete structures. Improper grounding can create stray currents that accelerate corrosion of the reinforcement. For this reason, it's important to follow the recommendations of a qualified electrical engineer when grounding metal components on near concrete structures. In summary, while some local code officials might interpret the codes as requiring grounding of precast foundation walls, a careful reading of the NEC, IPC, and ACI standards reveals no explicit requirement to do so. As long as other grounding provisions are in place, such as grounding electrodes and a properly grounded electrical system, grounding precast foundation walls is usually not deemed necessary. Always consult with local code officials and qualified engineers to ensure compliance with all applicable regulations. The NEC provides specific guidelines for grounding and bonding electrical systems to ensure safety and prevent electrical hazards. It outlines the requirements for grounding electrodes, grounding conductors, and bonding of metal parts to create a low impedance path for fault currents. This helps to minimize the risk of electric shock and equipment damage during electrical faults. The NEC also addresses the grounding of sensitive electronic equipment to protect it from voltage surges and electrical noise. Proper grounding can improve the performance and reliability of electronic systems by reducing interference and preventing data loss. The International Building Code, or IGC, establishes minimum requirements for building design and construction to ensure public safety and welfare. While it does not explicitly address the grounding of precast foundation walls, the IBC emphasizes the importance of proper electrical installations and compliance with the NEC. It requires that electrical systems be designed and installed in accordance with the NEC to minimize the risk of electrical hazards and ensure the safe operation of buildings. The American Concrete Institute, RSI, provides standards and guidelines for the design and construction of concrete structures, including precast foundation walls. While ACI standards do not specifically address the grounding of these walls, they emphasize the importance of proper reinforcement, detailing, and concrete mix design to ensure the structural integrity and durability of the foundation. Understanding the relationship between grounding, corrosion, and reinforced concrete is crucial for ensuring the long-term performance of precast foundation walls. Stray currents from improper grounding can accelerate corrosion of the reinforcement, leading to structural weakening and premature failure. Therefore, it is essential to follow industry best practices for grounding and corrosion protection when designing and installing precast foundation walls. The role of qualified engineers and code officials in interpreting and enforcing electrical and building codes is critical for ensuring the safety and compliance of precast foundation wall installations. These professionals have the knowledge and expertise to assess the specific conditions of each project and determine the appropriate grounding requirements based on applicable codes and standards. Their involvement can help to prevent potential electrical hazards and ensure the long-term performance and safety of the foundation system. When evaluating the need for grounding precast foundation walls, it is important to consider the specific characteristics of the soil and the surrounding environment. Soil resistivity can affect the effectiveness of grounding systems, and corrosive soils can accelerate the deterioration of grounding electrodes. Conducting thorough site assessments and soil testing can help to determine the appropriate grounding methods and materials for each project. Ultimately, the decision of whether to ground precast foundation walls should be based on a comprehensive assessment of the applicable codes, industry standards, site-specific conditions, and the recommendations of qualified engineers and code officials. By taking a holistic approach and considering all relevant factors, it is possible to ensure the safety, compliance, and long-term performance of precast foundation wall installations. The NEC provides guidelines for size and grounding conductors based on the size of the service entrance conductors. The grounding conductor must be large enough to safely carry the maximum fault current that could occur in the electrical system. Improperly sized grounding conductors can overheat and cause a fire or electrical shock hazard. The NEC also addresses the use of ground rods and other grounding electrodes. Ground rods must be installed deep enough to make good contact with the earth and provide a low impedance path to ground. The number and spacing of ground rods may vary depending on the soil conditions and the size of the electrical system. In addition to grounding, bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between metal parts, which can cause electric shock hazards. The NEC requires that all metal enclosures, raceways, and equipment be properly bonded to ensure electrical safety. The International Building Code, or IGC, references the NEC for electrical requirements. The IBC requires that electrical systems be installed in accordance with the NEC and other applicable standards. This ensures that buildings are designed and constructed to be electrically safe. The IBC also addresses the fire resistance of electrical systems. Electrical wiring and equipment must be installed in a manner that does not compromise the fire resistance of walls, floors, and ceilings. This helps to prevent the spread of fire in the event of an electrical fault. The American Concrete Institute, or RSI, provides guidance on the design and construction of concrete structures. ACI standards address the protection of reinforcing steel from corrosion. Corrosion of reinforcing steel can weaken concrete structures and lead to premature failure. ACI standards recommend the use of corrosion-resistant reinforcing steel, concrete admixtures, and other techniques to protect reinforcing steel from corrosion. The grounding of electrical systems can also affect the corrosion of reinforcing steel in concrete structures. Stray electrical currents can accelerate the corrosion of reinforcing steel. For this reason, it is important to properly design and install grounding systems to minimize the risk of corrosion. When evaluating the need for grounding precast foundation walls, it is important to consider the local soil conditions. Soil resistivity can affect the effectiveness of grounding systems. High soil resistivity can make it difficult to achieve a low impedance path to ground. In areas with high soil resistivity, it may be necessary to use multiple ground rods or other grounding electrodes to achieve adequate grounding. It is also important to consider the potential for stray electrical currents in the area. Stray electrical currents can come from a variety of sources, including nearby power lines, electrical equipment, and underground utilities. These currents can accelerate the corrosion of metal structures, including reinforcing steel and concrete. If stray electrical currents are present, it may be necessary to take additional measures to protect metal structures from corrosion. These measures may include the use of cathodic protection systems or other corrosion control techniques. Ultimately, the decision of whether to ground precast foundation walls should be based on a comprehensive evaluation of the applicable codes, industry standards, site-specific conditions, and the recommendations of qualified professionals. By taking a thorough approach and considering all relevant factors, it is possible to ensure the safety, durability, and long-term performance of precast foundation wall installations. The purpose of grounding is to provide a low impedance path for fault current to return to the source, which helps to trip the circuit breaker or fuse and energize the circuit. This protects people from electric shock and prevents damage to equipment. There are several types of grounding systems, including equipment grounding and system grounding. Equipment grounding connects the metal parts of electrical equipment to ground, while system grounding connects the neutral point of the electrical system to ground. Both types of grounding are important for electrical safety. The NEC provides specific requirements for grounding different types of electrical systems, including alternating current, or AC systems, and direct current, or DC systems. The requirements vary depending on the voltage, current, and type of equipment. It is important to follow the NEC requirements carefully to ensure electrical safety. Bonding is the process of connecting metal parts of electrical equipment and systems together to create a common ground potential. This helps to prevent voltage differences between metal parts, which can cause electric shock hazards. The NEC requires that all metal enclosures, raceways, and equipment be properly bonded. The bonding conductors must be sized according to the NEC requirements. The International Building Code, or IG, references the NEC for electrical requirements. The IBC requires that electrical systems be installed in accordance with the NEC and other applicable standards. The IBC also addresses the fire resistance of electrical systems. Electrical wiring and equipment must be installed in a manner that does not compromise the fire resistance of walls, floors, and ceilings. This helps to prevent the spread of fire in the event of an electrical fault. The American Concrete Institute, or ASI, provides guidance on the design and construction of concrete structures. ACI standards address the protection of reinforcing steel from corrosion. Corrosion of reinforcing steel can weaken concrete structures and lead to premature failure. ACI standards recommend the use of corrosion-resistant reinforcing steel, concrete admixtures, and other techniques to protect reinforcing steel from corrosion. The grounding of electrical systems can affect the corrosion of reinforcing steel in concrete structures. Stray electrical currents can accelerate the corrosion of reinforcing steel. For this reason, it is important to properly design and install grounding systems to minimize the risk of corrosion. When evaluating the need for grounding precast foundation walls, it is important to consider the local soil conditions. Soil resistivity can affect the effectiveness of grounding systems. High soil resistivity can make it difficult to achieve a low impedance path to ground. In areas with high soil resistivity, it may be necessary to use multiple ground rods or other grounding electrodes to achieve adequate grounding. It is also important to consider the potential for stray electrical currents in the area. Stray electrical currents can come from a variety of sources, including nearby power lines, electrical equipment, and underground utilities. These currents can accelerate the corrosion of metal structures, including reinforcing steel and concrete. If stray electrical currents are present, it may be necessary to take additional measures to protect metal structures from corrosion. These measures may include the use of cathodic protection systems or other corrosion control techniques. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the overcurrent protection device protecting the circuit. These tables ensure that the grounding conductor is large enough to safely carry the fault current. The NEC also provides requirements for the installation of grounding electrodes, including ground rods, ground plates, and underground metal water pipes. The grounding electrode must be properly installed and connected to the grounding system to provide a low impedance path to ground. The International Building Code requires that all electrical work be performed by qualified individuals who are licensed or certified to perform such work. This helps to ensure that electrical systems are installed safely and in accordance with the applicable codes and standards. The IBC also requires that electrical inspections be performed to verify that the electrical system meets the code requirements. These inspections are typically performed by local building officials. The American Concrete Institute recommends that concrete structures be designed and constructed to resist the effects of corrosion. This includes selecting appropriate materials, using proper construction techniques, and providing adequate protection for the reinforcing steel. ACI also recommends that concrete structures be inspected regularly to identify any signs of corrosion. If corrosion is detected, it should be repaired promptly to prevent further damage. The decision of whether to ground precast foundation walls should be made on a case-by-case basis, taking into account all of the relevant factors. There is no one-size-fits-all answer to this question. The best approach is to consult with qualified professionals, such as electrical engineers, structural engineers, and building officials, to determine the most appropriate grounding strategy for the specific project. By following this approach, it is possible to ensure that precast foundation walls are installed safely and in compliance with all applicable codes and standards. It is also important to consider the long-term maintenance of the grounding system. Grounding systems can deteriorate over time due to corrosion, mechanical damage, or other factors. It is important to inspect the grounding system regularly and perform any necessary maintenance to ensure that it continues to function properly. This may include replacing corroded grounding electrodes, repairing damaged grounding conductors, or tightening loose connections. By maintaining the grounding system properly, it is possible to ensure that it continues to provide adequate protection against electrical hazards for the life of the building. In addition to following the codes and standards, it is also important to use good engineering practices when designing and installing grounding systems. This includes considering the specific characteristics of the site, the type of electrical equipment being used, and the potential for future changes to the electrical system. By using good engineering practices, it is possible to design and install a grounding system that will provide reliable protection against electrical hazards for many years to come. The NEC requires that all electrical equipment be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or OL. This helps to ensure that the equipment meets safety standards and is suitable for its intended use. The NEC also requires that electrical equipment be installed in accordance with the manufacturer's instructions. This helps to ensure that the equipment is installed correctly and will function properly. The International Building Code, or IBC, requires that buildings be designed and constructed to resist the effects of natural disasters such as earthquakes, hurricanes, and floods. This includes designing the foundation to withstand the forces of these disasters. The IBC also requires that buildings be designed and constructed to be energy efficient. This includes using energy-efficient materials and equipment and designing the building to minimize energy consumption. The American Concrete Institute, or ASI, recommends that concrete structures be designed and constructed to be durable and long-lasting. This includes selecting appropriate materials, using proper construction techniques, and providing adequate protection against environmental factors such as moisture, temperature changes, and chemical attack.